This week we're learning all about density, which is a measurement of how much stuff fits in a certain space. And when we say how much stuff, we really mean how much matter. Fits in a certain space. And like I said, that stuff is atoms, molecules, it's just matter. We'll talk more about that in a sec. Matter is what we're talking about, and how much of a certain amount of matter fits into a certain space, that will determine its density. So it's a ratio of mass to volume, and you guys, we've learned unit rates together in class, but that's kind of what density is it's a unit rate of the mass and volume. And in science, mass is measured in grams, and volume is measured in milliliters, just like you see there. Okay? So the way that we calculate or find the density is we're going to write a formula, an algebraic formula for ourselves. So D stands for density, which equals mass divided by volume. I'm going to write this a couple different ways so that we can remember what each of those things stands for. But density equals mass divided by volume. So like I said, it's a unit rate that compares or equates the mass and the volume. When we find mass in science, it's a pretty easy thing to do. We're just going to use a scale. It really is as simple as just placing it on the scale. Use a scale, which we've used in class together. So that's pretty easy. But what can be trickier, though, is finding the volume. And we have some strategies about how to do that with a rectangular prism. We know we're going to do length times width times height. But not everything is a rectangular prism. Pretty much it comes down to like a fish tank and a box of Kleenex. Those are the things that I can think of that are rectangular prisms. And when we're finding volume of objects in order to find their density, oftentimes we have really randomly weird shaped objects, like a desk has kind of this rectangular piece to it, but it also has those 4 legs. So we're going to use a different strategy. Oh, and by the way, something you can look forward to next year about for 7th and 8th grade math, in order to find volume of a sphere, a regular perfectly shaped sphere like a basketball, you're going to do this formula, 4/3 pi times the radius cubed. So as we can see, formulas for volume can be kind of messy, like this one, or maybe a little bit easier to work with, like this one. But oftentimes the objects that we're dealing with, if we want to find their density, maybe don't fit into one of these 2 boxes, right? It's not, there are even volume formulas for all kinds of things that we're not going to bother with at all. So instead, we're going to use what's called the water displacement method. And we'll practice this, this in class. This is called the water displacement method. Water displacement method. And this would be how you would find the volume of like yourself. How much space does your body take up? That's different from your weight or your mass. Your volume is how much physical space do you take up. And since your head isn't exactly a sphere and the rest of your body isn't exactly a rectangular prism, we need to use a different strategy in order to find our volume. So here's how the water displacement method works. If an object is submerged, like completely covered in water, then here, I guess let's draw, this will be fun. I want you guys to also draw as we talk about the water displacement method, draw a bathtub. And then, draw a bathtub, and then draw a guy chilling in it. Take a minute to make that look a little bit better. Draw a bathtub. And I'm going to draw a stick figure here to represent this guy chilling in the bathtub. Okay, great. So when he's in the bathtub, or before he gets in, let's say that the water is here, right? Or maybe right now, right where he's halfway submerged, the water is up to there. When he sinks his whole body in, let's say he submerges himself, and now he's completely under the water. He takes a big breath, sinks himself completely in the water level is going to rise up a little bit, and you can test this for yourself in the bathtub. The water level is going to rise as he sinks his whole body in. And the volume of his whole body is however much it rises. So let's see. This is going to be the volume of his body, which I know sounds kind of weird. So let's say before he gets in at all, is this pink line. That's before he even steps a toe in the water. If he gets in and he sinks his whole body down, the new level is here. The exact volume of this water, however many milliliters or liters that is, the exact volume of the water that's displaced is the volume of his body. And this is called the water displacement method. Another way to think about this is if we, let's say, had a graduated cylinder like this. You guys remember these? Graduated cylinder maybe is here with water to start. When we add, let's say, an M&M, if we add an M&M, then the volume of the water is going to rise a little bit. Maybe it's up here now. This distance right here is the exact volume of the M&M. That's called the water displacement method. The exact amount of space that was taken up by the M&M is the exact volume of the water that was displaced. So that's pretty cool. That's called the water displacement method. When an object is submerged in water, the fluid displaced, the amount of water, the amount of fluid displaced or moved is equal to the volume of the object. And we've got two good examples here. Okay, so that'll be one way that we can use to find the volume of irregular objects. Like I said, if it's a rectangular prism or a sphere, we've got some easy formulas for how to do that. But if it's something that's weirdly shaped, like an M&M or a person, we're going to use the water displacement method instead to find the volume. Okay. So then just a reminder too that that volume is just a piece of our formula here, and our formula is density equals mass divided by volume. Once we found our volume, we're going to plug it into this formula here. So anyway, once we've done that, we'll have a mass using a scale and a volume that we've gathered from how much space was, or how much water was displaced. We're going to do mass divided by volume, and we're going to come up with a certain number. So let's try that, for instance, with water. Let's say, and we'll just use a graduated cylinder to measure the volume of the water. Let's say that water, oh my goodness gracious. Let's draw ourselves an example here and practice finding volume. Ooh. Awesome. Okay. Let's do mass in this column, volume there, and then density here. So if we used a scale, let's say we put a graduated cylinder on a scale, and we poured 25 milliliters of water into it, into the graduated cylinder, we would expect that the mass of the water that's in there would be 25 grams. So in order to find the density, we just do mass divided by volume, or 25 over 25, which just makes 1. So 1 is our answer there for the volume of water. Let's say we put 100 milliliters in a graduated cylinder, 100 milliliters of water, and then we put that water on a scale. We would expect the water to weigh 100 grams. So again, we would do 100 divided by 100, mass divided by volume, which gives us a density again of 1. Let's do one more, and I'll leave it blank for you guys this time. Let's say you had a 75 gram sample of water that filled up to 75 milliliters on the graduated cylinder. What would you expect its density to be? Okay, so now that you've got some more practice with finding density, one thing that we'll see this week is this idea of sinking and floating. So if you tossed a sponge into water, you would expect the sponge to float, unless it was SpongeBob, in which case somehow he sinks. I'm not quite sure how. But you'd expect something really light to float in water. And when I say light, I guess I mean less dense. The less dense object floats, and the denser, or not heavier, but denser object sinks. So if, like again, this M&M that we threw here in this sample of water, the M&M sinks in the water, therefore the M&M is denser because it sinks. The water is less dense because it's, in a sense, floating around and above the M&M, if that makes sense, which is kind of a weird idea. Okay. So the last piece on this is that density is a characteristic property. That's an important idea. Characteristic property, which means that it's not going to change as long as we're looking at the same sample or the same substance, say for water, for instance. It's going to have the same density always. Water is always going to have the same density. Salt water is a little bit different. That's made up of different things, so that has a different density. But density is a characteristic property, which means that the size, let's say volume, the volume and mass doesn't matter, or doesn't affect, let's say, doesn't affect the density. The density won't change. A little slower. The density won't change because density is a characteristic property. Other examples of characteristic properties are the fact that water freezes at 32 degrees and it boils at 212 degrees. Those are characteristic properties. And the fact that water has a density of 1 gram per milliliter, that is also a characteristic property. It's not going to change whether we have 25 grams of water, 100 milliliters of water. Its density is never going to change. It's always going to be 1.